Okay. So this is where we stopped last time. Remember what happened? Okay. So remember, multiple imputation variance estimator has this form W and B. So basically, the idea is we are interested in computing the variance of the MI, which can be written as, so if we can write it, so idea is this will be estimated by WM, and this will be estimated by WPM, right? So that is the big picture idea. But there's actually one thing we missed here. What is missing? So the implicit assumption is that the covariance is 0. There's a covariance actually, right? The covariance between the two terms. So the covariance is 0 when if the model, so if MLE is used. So that's the one important message that was neglected in Rubin's original idea. So Rubin has a very interesting idea, but what he missed is this covariance, and so actually, this fact was found by me. So I figured out what he missed in his paper, and that was actually quite highly viewed paper at JRSSB 2016 6. So anyway, so I cannot really cover all the details, but I'm gonna briefly show you the steps. Okay. So so end of the day, okay. So remember, okay. So this one basically is variance of the eta hat n, right? And this one, so what we'll show is that this one is variance of the eta hat mi minus eta hat n. Okay, I think this is, well, this one is an assumption, right? I mean the W, but this is not assumption. This is true, right? This is for sample size n. This is the complete sample variance estimator. So variance. So that is true. But what we can assume is that if, right? If so, this is actually part of the assumption in theorem 5.2. So assumption here is that Wm estimate the variance of the at head n. Okay. And then now we wanna evaluate that we wanna evaluate the second term of 11. Okay. So to simplify this, so basically to understand this term, second term, what we want to use this matrix algebra. Sometimes this matrix algebra is called Woodbury matrix identity. Okay. So this is basically matrix algebra formula, and you can use this one again, apply the same formula again, and put it, right? Put it to here. So this one can go inside and then simplify. So if you insert this one into here, and then apply, then you have this form. Okay, and then basically we use this A equal I, B equal I, and C. Then this will be, so A is I, B is what? I. So I. And C is what? I miss, minus I miss. Okay. So, and I, right? So then this one is what? Inverse of I, minus I miss, which is the inverse of the I obvious. Okay. So that basically we wanna express this inverse of I, expand. And then this one is what? I, inverse, right? And so to all this, then you end up getting this one. So I obvious inverse is I, inverse plus some of the two terms. And then see, these last two terms are actually what we see. We have seen in 11. Okay. So these two last terms is nothing but I, obvious inverse minus I, okay. So, well, actually it's 11. So this is not really good. So this is actually should be. So this one should be I. Oh, sorry. I see. Okay. Never mind. So what is 11? 11 is this one. So that means you have, so let's expand this 1 plus 1 over m with this, the second term, right? So let's extend it, this one, m plus 1 over m times this one. And then the first term is actually some of the three terms, this guy, and this guy. That is actually this one. Okay, by 12. You know what I mean? So, okay, 11 is basically, let me write it down. So 11 is I, inverse plus 1 over m, and then these two, J miss I obvious inverse, J miss prime plus I, inverse I miss I, inverse, right? Okay. So my point is that you can actually write it, expand it to get the, so that is basically is EBM plus 1 over m expectation EBM. And then this guy is equal to I obvious inverse by 12. So that's basically proving the asymptotic unbiasedness of the Rubin's variance estimator. Yeah. 2 pages before? Yeah, and 1 page before. Maybe here. Okay.
So that is equal to 0, right? So is this also true for single imputation estimate?
So are you questioning about this one or?
No. The notes that you write, you said in the GIS paper.
Oh, I see, okay.
I'm asking whether that is also true for single imputation estimate.
Yeah, actually, so there's actually typo. This should be n. So basically, I think I should write it. Let me first. Yeah, and I think I have a typo. So let me write it more clearly. So variance of the eta hat mi, which is actually, you're right, doesn't have to be, m can be equal to 1. Okay. So then you can write it as a n plus, so I guess the point is you can write it as a n plus eta hat mi minus eta hat n. And so you can write it n plus variance of the eta hat mi minus eta hat m plus 2 covariance eta hat n and eta hat mi minus eta hat n. Okay, so the theorem, this theorem 5.2 basically says this is expectation of the Wm, and this one is actually expectation of 1 over m times variance expectation of Bm. So what we showed is this one. And this one, so this one, it can be shown to be 0 if MNE is used. So you're right. The result is actually true even for m equal to 1. Even though if n equal to 1, then Pm is not really defined. But the variance, the decomposition still.
Yeah, I mean, so if we do not use the Bayesian to do imputation, we just use the NAE.
Okay.
Like single imputation.
Right.
So whether this is also true.
That's a very good point. I think I don't think so. So because see this part appears because of the Bayesian implication, because of the posterior generation, and second part is actually genuine prediction. So this one is appears here because of the Bayesian implication, and what we used is to use this identity to show the unbiasedness, right? I mean, to show unbiasedness. So if we don't have this one, right? If we don't have this one, then we don't have, so the Rubin's formula does not work.
Right. So but if we think the Bayesian approach as if we think the single imputation, the frequentist approach as a extreme case of Bayesian approach, okay. So we basically just sample as the estimates, like the point mass distribution. So in the Bayesian, so in the series, I didn't see any conditions to prove for that case. So I'm thinking whether the frequentist case can be covered in those theories.
The frequentist case?
The frequentist approach, like just sample as the estimate.
So I think what is assumed behind with the Bayesian imputation is that this guy is actually computing this one, which is actually so this one, second term is more like a Pythagorean. right? Pythagorean theorem, decomposition. And first one is actually using Bayesian. So if you don't have a Bayesian, then we don't have this identity. So actually, I got this idea. I mean, this JRSSB paper idea of when I about to graduate, I get a PhD in 2000, and then when I point out that something's not really correct in multiple imputation, nobody believed me because Rubin cannot be wrong, right? I mean, that's all the responses I heard. So I first spent a lot of time persuading Dr. Fuller, to understand why the multiple imputation is not really has some problem, and then we started writing paper. So anyway, so even though we cannot really trust someone by just the name, right? You should always question and try to check and make sure you understand it. Otherwise, you just believe it, right? I mean, so anyway, that was so that was kind of interesting event for me. So now I'm gonna move on. Is it okay? So does it answers to your question?
Yeah.
Okay. Okay.
Yeah, but which one you prefer, the multiple imputation and single imputation?
Huh?
Which one you prefer? Now, the multiple imputation.
I think multiple imputation is okay as long as we understand its limitation, right? We understand that the limitation is that it's only applicable to MLE, so it doesn't really applicable to method of moment estimator, other estimators. It's not really true. So as long as we understand its limitation, multiplication is actually very attractive, very easy to use, and so.
Also, I have two questions regarding your comment. So in the proof that you talk about, it looks like the MLE is only used. It's only used in the proof, right? You decompose the estimate into two parts.
Okay.
And then you derive the variance based on that expression. It's actually not used in constructing the estimator.
Well, actually, that's a very good point. Actually, I did use it. So the whole, so this A, right? The equation A, result A, is actually derived from solving the score equation. Okay, imputed score equation. So it assumes that I'm interested in MLE. So I'm going to use M. Okay. So let's move on. So that is actually the basic theory for first part of the theory of multiple imputation. And so we have 3 examples. So the next, this part is overlap. The first example is overlapping. So I just presented in this separate slide. So this is the simplest. So normal mu sigma square, and first R elements are observed and the remaining n minus R elements are missing. And then response mechanism is missing a random. And then in this normal case, right, normal example, we can use Bayesian imputation with inverse gamma prior and posterior. This is posterior, right? And then you have so you basically you generate sigma first and then generate mu, and then from mu and sigma you generate y star. So that is the Bayesian imputation, right? Okay, and then MI point estimator is just the of the mean is just this one, and then let's take a look what's going on. So we have two things going on. This is a posterior step. So you generate the parameter, and then given the parameter, you generate imputation. So we can express this multiple imputation estimator and decompose into three terms, right? The MLE part, and then this is a posterior part, and then this is the imputation part, right? Like what we did in the so in the previous slide, equation 8 corresponds to this decomposition. Let me briefly go back to what 8 is. So this one, right? So we have these three terms. So these three terms, we already see that these three terms are independent, right? Orthogonal. So that applies the same specifically to this example. We have the same structure. So then this is the MLE part, right? Zeta hat MLE. And then this one is a kind of eta star J minus zeta hat MLE. And then we average over. And then we have something like I miss what is 8? Let me go back. Yeah, J miss. Sorry, J miss. Okay. J miss. So J miss should corresponds to n minus r divided by n. Because what is J miss? J miss is ICOM inverse I obvious, right? Sorry, I'm right. I miss, right? So ICOM is n times in this case sigma square, right? I miss is n minus r times sigma square, something like that. So this one is a J miss. Okay. And then you average them over J. And also you can another way is you can check whether the right side is simplifies to MI, right? So, okay. Another way is you can, you cannot just believe this, right? We can actually check. We need to check. So what is eta hat MI? Eta hat MI is J equal to M, J equal to 1 to M, zeta hat I, J. That's exactly this one. And then this one is what? Delta I, yi plus 1 minus delta I, and then mu star J plus yi star J minus mu star J, something like that. So basically, this guy is average of m imputed values, right? And that actually, so you have this one. So delta I equal to 1, you don't do anything. You have just observed 1. Delta equal to 0, you have imputation. So imputation is actually you first generate mu j star and then generate error, right? Okay. So that's basically what's going on here. So I think. And then this guy, I see. This guy is also written as y bar r plus, because of the posterior step, r, right? So you have three terms basically: y bar r, posterior part, and then arrow part. You have three parts. So then you can simplify. That actually gives the y bar r plus this one, m minus r. So basically, the first part take care of the y, this guy plus this guy. Does that make sense or not? Okay, let's do one more time. So one by one. So that is actually, you can write it this way. So you can write it as a n y bar, because here you have a r over y bar r. Summation of delta y is r times y bar r. And then you have a, then second term is m minus r times y bar r. You have a m minus r of them, right? So you have this. And then plus m minus r mu star j minus y bar r plus the error term. Okay. Well, and then your last term has a summation over I equal to r plus 1 to n by I star j minus j. Okay. It's just algebra, but you basically you can also analyze, and then this guy can be merged with the y bar r in the respondent. So that's how you get three terms, and these three terms are independent. So with the variance, first term is variance 1 over sigma squared divided by r. Second term is variance of this one. The third term is variance of this one. And so you can combine them. Okay. And then now this is about, so this is about the point estimator, variance of the point estimator. And then to discuss variance estimation, we need to first check whether this assumption is satisfied. So that's the step. So we'll check whether this assumption is satisfied. And then second step is we want to check whether this assumption, which is actually variance of the y bar. Yeah, that is actually what eta hat, theta hat mi, theta hat n. So we'll check on this one by one. Basically, the idea is I'm not going to discuss all the details, but this one is basically quadratic function. of data, imputed data, right? You have a quadratic function. So then the expectation when you can, as long as you know the correlation structure, covariance structure, the expectation of the quadratic function should be computable. Exactly. And so this is what you can do. You can some simplification here, like subtracting the mean and just algebra. But at the end of the day, what you can see is that this one dominates and the second term is negligible order. So you can get basically this basically proves the first part of the theory. And then second part, it's the same story, but you can see what is the y bar mi end of the day. That is essentially y bar r. I mean, approximately. And then, so this guy is actually y bar r minus y bar n. So that is actually what? So that is actually, what is the variance of the y bar r minus y bar n is variance of the y bar r minus variance of the y bar n. So that is 1 over r minus 1 over n sigma square. That is actually, I think this one. So to see, let's see. Yeah, right, this one. Yeah. So you can check several different ways, but this is probably the easiest way. So basically, this example shows of the property satisfies the assumptions for theorem 5.2. So confirms the asymptotic unbiasedness of the Rubin's variance estimator. Okay. And another one, which is kind of interesting, is Bayesian bootstrap. Probably you heard about Bayesian. Yeah. Figures, okay. Here or
Yeah, so you need to show that. So in the condition for theorem 5.2, there is a condition say that the imputed data, the variance of imputed data is asymptotically equivalent to the variance of the
complete sample.
the complete sample.
Right.
Right. So usually that condition should satisfy, right? So if
Should be satisfied, right?
if the model is correct, because you basically generate under the correct model.
Yeah.
Right? So that is a natural condition if all the models are correct. If the sample size go to infinity, right? So
Yeah, that's a good question. So actually, imputation introduced the correlation between data. So there's a and make sure. So basically, the original variance estimator, right? Remember, what is this? This guy is 1 over n s squared, right? And this guy is based on the assumption that data, the elements are independent, IID, right? But after imputation, our data is no longer IID. They are correlated.
Right, but the correlation is due to the estimates.
Due to estimation, right?
Right, but if the sample size goes to infinity, the estimates converge to the divided.
Exactly. That's right. Yes.
It's kind of asymptotic is independent.
Yeah. Right. That's a very good point. That's exactly what I proved in the paper. So basically asymptotically, the covariance correlation doesn't really contribute to the main term. So this is a very weak condition. I mean, so will be almost always satisfied. Yes. Yeah, that's very good. Yeah, thank you. So yeah, if you are curious, you are welcome to check my 2006 paper. Anyway, let's move on. So so this is a very interesting idea, and that actually becomes very hot research topic in Bayesian, non-parametric Bayesian, because it's kind of doing non-parametric inference in a Bayesian way. So the idea is, okay, suppose we assume the sample given, and then the point mass associated with the data, observed data, is can be non-parametrically modeled as a P multinomial. So P1 to Pk, I mean P1 to P, right? So, and then this is essentially Dirichlet type distribution, and then I mean multinomial distribution. Sorry, and then the idea is the novelty is that we treat y as given. Okay, so y is fixed. So we have the values of y is fixed, and what is not fixed in Bayesian sense is p, the point mass. So then this is your parameter, right? Your parameter is just so because you know the support. This is known. This is unknown. So your parameter can be referenced this way. And so the problem reduces to estimated P. Okay. And so his idea is use Bayesian. And so the idea is use prior. So this is a prior distribution. And then posterior with this multinomial will be Dirichlet. And so the posterior, and then the posterior expectation will be the mean of Dirichlet. And then let alpha all equal to 1. So this is actually is equal. So if you let alpha all equal to 1, that is actually uniform, right? So your prior is uniform, non-informative, but you can still do posterior. So the uniform you don't have actually it's just disappears, right? But the posterior you have some Dirichlet form. And so and then the interesting part is he then set alpha equal to 0 and k equal to n. That means what? It's like a Bayesian way of doing bootstrap. So what is the bootstrap? Suppose you use, okay, y12, you have a 1 to r. Okay, so if you just do bootstrap, you have a 1 to r, and then r plus 1 to n, right? And you have an observation y, and you don't know. If you just do bootstrap, then you just do this way, right? You just choose each one. You choose one at random and then replace. That is actually kind of generating imputation from p hat MLE. if you do bootstrap, okay, if you do bootstrap, you are actually you use the amplified distribution of the observation, and from there you select one. But this is a frequentist. You can see that this is, if you use this one, this is a frequentist. So the Bayesian way is you first generate. So you generate P star from posterior, and then generate Y star from P star. Okay, that is the Bayesian, right? And then Lubin move on further to develop this interesting idea. So basically, he has a this is actually Bayesian, and then the next one. Okay, so this is basically here. So step one is this one. Generated from Dirichlet distribution with parameter one, and then step two from P star, you select one.
So I think from step one, it seems like
Huh?
from step one, the statement of step one it seems like it generated from trial instead of the theory.
Actually, that is the Lubin's Bayesian bootstrap is the Bayesian using, so if using this alpha equal to 0 as a prior. So if you use alpha equal to 0, then posterior it becomes 1. That's interesting. And then basically that they really create this, that's actually kind of uniform, right? Uniform. But with that you generate. And then basically this is the multiple imputation. So it's like a Bayesian way of doing bootstrap, rather than just generating bootstrap sample from MLE, generating bootstrap sample from posterior. And he claimed that this is better, and turns out that we can check. So turns out that you end of the day, okay, if you do so this method seems to be totally different from Gaussian, right? The totally different way of generating imputation from normal distribution, but asymptotically they are equivalent. So this, okay, this variance 4 is exactly the same as the variance we have here, 1. Okay, asymptotically, okay, not exactly the same, but asymptotically, at least the up to the main term of the variance, this formula 1 and this formula 4 are equal. So the Bayesian bootstrap method is asymptotically equivalent to that under normality. And this paper, Lubin and Schenker propose an approximation of the Bayesian bootstrap called approximate Bayesian bootstrap, which provides an alternative approach of generating imputed values from empirical distribution. So, okay, so this is, remember, this is a P step, right? And this is P step, and this is the I step. But you can see that this P step is actually viewed as a generating population. And then from the generated population, you draw a sample. So that is actually another way of viewing this problem. So basically you use this one, given YR, given YR, you generate the donor set, which is a kind of population. So you just do a bootstrap once, and then from there, you generate another bootstrap second. And this is your imputation data. That turns out to be exactly approximately the same as Bayesian bootstrap. So that's why we call it ABB. So approximate. So the difference, okay. So basically the idea is to give some perturbation, right? To give some randomness in drawing imputation. And rather than using fixed one, you draw randomness here. But you can draw the randomness by doing bootstrap twice. You have a bootstrap once and bootstrap second. At the end of the day, you have the same. So basically you have a Y1, YR, and then you want to create YR plus 1 to YN, right? So rather than just drawing once, let's do in the Bayesian way, we need to do it, create randomness 2 times. So first draw, right? First draw randomness to get Y1 star to YR star. That's the first step. And from there, you draw imputation. Okay. Okay. You mean the here? Okay. We assume missing at random. Okay. So you're not really. I mean, even the normal imputation, right? Remember, in the normal imputation, we don't really use any assumptions on the response mechanism other than missing at random. So basically, we just use the same, assume that 2 samples, right? The respondent and non-respondent follows the same model. Okay.
And this multiple imputation can be used for if you have all the models. Can be used for
Sure, yeah. So this idea, I mean, the example here, all assume the missing at random, but you can still apply to non-uniform missing, as long as you need to, as long as you can generate the posterior values of the parameters in the model.
And for looping, Bayesian bootstrap approach, if there is covariance, can they account for the effect of covariance? If it's missing at random, but it's given covariance.
I think, yeah. So this the paper here is a kind of unique, but this idea has been explored a lot in the Bayesian community, and so David Dawson developed some extension of OW. I don't know the only details, but yeah. But so that this paper actually opens up kind of a non-parametric Bayesian ideas, because it doesn't seem to use any model assumption, right? Other than just empirical. So it's very ingenious idea. I think this idea actually developed right after Efron's bootstrap. So Efron write a paper on bootstrap 1979, something like that, and then Rubin says that where there may be a Bayesian way of doing bootstrap. So that's this one. So anyway, double. This is actually kind of double bootstrap, right? Right. So the first bootstrap. So my interpretation is you can, rather than generating respondent to non-respondent. You can generate respondent to reconstruct your population. Reconstruct your final population, and then from there you can generate, right? Because you are essentially you are using the same model, so then they must have a same population, and so we need to reflect the uncertainty in constructing our population, something like that. Okay, so that basically take care of the Bayesian bootstrap. Actually, my second paper is to view that this R is a tuning parameter. You don't have to choose this R. You can actually choose K. You can do bootstrap K, and then from K to right to the bootstrap. So the mechanism of double bootstrap remains the same, but you can actually choose this size to be general and then try to optimize it. It is something. So that is actually kind of my first biometric paper. So anyway, let's move on. So normal regression. So regression model is this one, and then so you have a first R units are responding, and so basically you can write it as a xn is xr xn minus r, right? So you have a x1 prime. Your first, right? You x2 xn prime. So that is n times p, n row and p column. So that so we want to do Bayesian way of multiple imputation and then develop the variance estimation. So remember in the complete response we can have inverse gamma generated from sigma square, and then so inverse gamma from generated sigma square, and then generate beta from normal with the sigma square from here, and then use that to generate imputation. So that's typical Bayesian imputation. And then in the case repetition of a multiple imputation, we can calculate the imputed version of the full sample estimators, something like this. So we have a first R, we observe the Y, and then from R plus 1 to N, we have a imputed data. Okay. And so then you can apply so use this imputed regression coefficient and then construct the multiple imputation, right? And then multiple imputation variance estimator. So basically, if you do that, you can write. So basically, you can decompose it through three parts. Your imputed value has a MLE prediction part, and then posterior part, and then error part, right? Imputation error part. And so you can plug into here and then simplify. Then you can end up getting 3 terms. And the first term is the beta hat R, which is basically MLE. The second part is essentially the imputation. I mean the posterior step. And so the part is the pure error part, imputation error. Okay. So that is very similar, right, to what we have done so far.
So the beta hat R is based on the observed data, right?
Beta hat R is right. So this one, MLE.
But in the expansion, that we talk about, which is based on the complete data part of the expansion.
We have to, so well, this is actually so in the monotone missing, remember, so you have a y equal x beta plus epsilon, right? And then you actually have a MAR. So and then you have a missing data. So you have a x1. You know what I mean? So you have x and y, 1 to r, y x1 to xr, y1 to yr, and then xr plus 1 to xn, and then missing. Okay. So in this case, in the missing data set up with the mode. So one result is that the MLE is equal to using the CC analysis. Oh. Okay. Okay. The MLE for regression function is exactly equal to the one that ignores the partial response in the covariance.
But that looks like the obvious maximize the obvious likelihood instead of the complete likelihood. So when you talk about the multiple imputation series, you said that the first term should be the MLE for the complete data, right? But here the MLE for complete data, at least I think the formulation is different.
Well, you mean that this one should be beta at n, right? I mean,
Right.
So, no, actually, that's not true. If you, okay, that's a good question. So actually, so I should make it clear that this, what I mean here is the MLE with missing data.
Oh, okay.
Okay.
Okay, but for the variance component.
Right. So I should make it clear. So the right. So yeah, that's so when I talk about the orthogonality, right? Am I equal to, yeah, it's really confusing because and then plus covariance is 0 to covariance is 0 if eta we use eta MLE on the complete response. So I should have a subscript n to emphasize that. So if we are going to use MLE as an estimator for applying imputation, multiple imputation. So that is different from the MLE that we talk about in the variance decomposition. Okay. Yeah. Yeah. Okay. So this is the MLE with the missing data. And then you have 3 terms. And also the 3 terms are independent. Oh yeah.
What was in that case?
You mean the okay. You mean the previous writing here. So this. So if this is a septa head, eta head, whatever septa or eta, and n is the variance on the no missing. right? And then you have a variance increase because of missing data. So after imputation, you are more likely to increase the variance, right?
So in your previous example, in the model missing example, model missingness example, eta hat n is MLE after accounting for the missing y values, right? So with the complete data.
Okay.
Yeah. Okay. So if you observe that there's missing y's, and then you apply MLE, then the other complete data.
Right.
That is
Right.
Okay.
Yeah, sorry, this is a little bit probably too much. But yeah, let's just move on. So then you can do some matrix algebra. So basically, conceptually, this is linear model. So you have three terms independent. So you can conceptually should be able to compute the variance. So the variance of the first term is this one, the first term here. And then it doesn't really look nice, but this h itself is something like this, and then you have h over the missing part, and so end of the day you get something like this, and so you can work out some linear algebra, matrix algebra to eventually show that this is what you get. But the result is it kind of makes sense. Basically, you have a variance of the MLE plus additional term, which is like a, so that exactly matches to my original decomposition, right? This is the variance of the beta hat n, and this is the kind of a variance of the beta hat mi minus beta hat n. And this beta hat mi minus beta hat n is attribute. Ah, thank you. Yeah, I think sorry, this is actually different. Okay, right. This is not really about variance estimation. That's right. This one is actually beta hat r, right? Nothing else. And this is turns out to be variance of the PM. I guess that's what we end of the day we show, and then basically we can check that Rubin's variance estimator can be established here. Okay.
But in this case, the variance of the market imputation is actually bigger.
Right. Yeah. So yeah, many people blindly use multiplication for the regression model, which is not really necessary because you can just do CC analysis, right? You can do CC analysis and easily compute the standard error too. I mean, why use multiplication at all? So well, I think Rubin's influence really is probably too high.
Like this one, like used in all the context.
And also he actually oversold it. I mean, he claimed that this will really save the world, and so many people just trust to what he said, and so blindly, use it without really thinking hard. So anyway, that actually give me a chance to write a good papers end of the day. So that's example. And then I'm not sure whether I have time to cover this day, but I will just cover it a little bit and then cover the remaining part in a separate YouTube lecture. So here's a motivation. So we have a model, and then the parameter interest. If the parameter interest is more like this form, you can actually come up with the two estimators, two different estimators. One is the MLE, and the other one is method of moment estimator, which is just a sample mean. Okay, so this one is MLE, and for the MLE with the n, we subscript n, we know MLE multiple imputation works, and so that now the question is how it performs with method moment. So that is the main question. So you have a method moment estimator. You can still apply imputation, right? You can still apply this Bayesian imputation and compute a multiple imputation estimator. The point estimator may be okay, but what about the variance estimator? So using Rubin's formula. So you can still compute it. Question is whether it's valid. It's a different story. So then you can easily check. So question is the MI variance estimator approximately unbiased for the variance, true variance? The answer is yes, if the variance satisfies this. And that is true if we have this one. So what I proved in my paper is that for many cases, so we proved this, but what is missing is a covariance, right? So then here's a very simple simulation example. You can check. So okay, for example, here's the simulation setup is a linear model, and you are interested in the population mean. Theta 1 is population mean of y, and theta 2 is the population proportion less than y equal to 1. So then in estimating theta 2, we used the method moment estimator on the complete response. And then in this case, the variance estimator of theta 2 will be just this one, because it's a proportion, right? So, and then multiple imputation with m equal 50 was used. And then after multiple imputation, Rubin's variance formula was used. And then this is the result. So basically, the point estimator itself is okay. The problem is variance estimation, the relative bias of the variance estimator. So relative bias means of variance estimator is the bias of the variance estimator divided by true variance. Okay. So in this case, so theta 1, no problem. We got a very small relative bias. But theta 2, we got 30% overestimation. So that, and then you can, the test statistic for zero mean is significantly large. So what's going on? Well, this is a really simple model, right? You have a regression model. So you can actually theoretically compute all the components. So you can actually compute. So in the setup, you have this one. I mean, theta 1. Theta 1 is just the sample mean, right? So in this cases, so sample mean case, you have a very nice decomposition. So which, and then I actually compute each component separately of the variance in the simulation. And then this one, so this is a simulation result. This is a theoretical result. And so this one actually matches, right? quite well. So then test the statistic is, so that means variance estimator is very good for theta equal to 1. Theta 2, we actually have a covariance. And so basically the covariance is ignored in Rubin's variance estimator, which gives overestimation. So variance, this is what Rubin's variance formula gives in expectation, and this is the true variance. Okay, so this is the true what you want to compute, and this is what you end up computing, right? And so that gives the shows the bias, and so okay, so that, I mean, you can easily do simulation and check that Rubin's variance formula does not really work, right? And so there's some, discussion and try to explain why, and then it took us some time to figure out really clearly, and so that's actually the theory that we developed with Su Yang later. So that's one of her part of the PhD thesis. So anyway, I will cover this theory part in the separate lecture notes. This is maybe too advanced, so you don't have to really worry about the details unless you are really interested. But anyway, I cover it in a lecture note, in the separate lecture, and then next week I will move on to chapter 6, which is fractional imputation. Okay.